So this is chapter 2, talking about the chemical level of organization. This is a pretty simple chapter. It's basically just general chemistry. If you've had high school chemistry or any kind of college gen chem, this is basically just that condensed down into one cute little chapter. So let's get started. There. So chemistry is just basically the science of structure and the interactions of matter. So matter is going to be anything that has mass and takes up space. So everything is basically made up of matter. And then mass, on the other hand, is going to be the amount of matter that a substance contains. Whereas weight is simply going to be the force of gravity that's acting on a mass. So weight is dependent on gravity. So that's why you weigh something different on Earth than what you would weigh on the moon. But your mass is going to be the same on Earth versus on the moon because it is not dependent on gravity. So, as you probably know, matter is going to exist in three forms. We have solid, liquid, and gas. A solid is going to have a definitive shape and a definitive volume. These are going to be things obviously like bones and teeth. These are hard. They're not going to change shape, essentially. Liquid is going to have a definite volume, and it's going to also then assume the shape of whatever container it's in. So it's not going to have a defined or a definitive shape. This is things like blood or blood plasma, the pleural fluid that's going to be around the lungs, etc. And then our final type of matter, or our final form for matter to exist in, is gas. And this is going to have neither a definitive shape or volume. So things like carbon dioxide, oxygen, the shape and the volume is going to vary depending on the size and shape of the container that it's in. So all forms of matter are going to be composed of various chemical elements. And each element in a substance is going to be something that cannot be split into simpler substances by any ordinary chemical means. Now, obviously, we have some extraordinary chemical means with technology these days, but for the purposes of this class, and each element of a substance is, like I said, each element is something that cannot be split into any simpler substance. So, elements are going to be given chemical symbols. Usually it's one or two letters, just to sort of, as a nice way to abbreviate what we're talking about. So oxygen is going to be O, carbon is C, hydrogen is H, nitrogen is N. Things like calcium is going to be Ca, so it's one of the ones with the two letters. And those four right there, the oxygen, carbon, hydrogen, and nitrogen, these are going to be the elements that make up the vast majority of your body. So, there are more than just those four elements in the body, obviously, but those are our major elements. So oxygen is going to make up about 65% of the total mass of the body. And then carbon is going to be 18.5% or so. So these are going to be, these four elements are going to make up most of your body. We then have elements that are present in the body but are going to make up a smaller portion of the body. All total, these elements are going to be about 3.6% of your total body mass. So this is things like calcium, phosphorus, sulfur, magnesium, iron. All of these are still really important, but they're just less abundant in the body. And then also we have these trace elements. These are going to make up about less than 0.5% of that total body mass. And again, these are still important molecules or elements that are important in your body, especially for a lot of signaling things, but they're just much less abundant. So the various chemical elements that make up our body are going to be composed of units of matter that are going to be called atoms. So these elements are made up of the same types of atoms. So atoms are simply the smallest unit of matter that's going to retain the properties and characteristics of an element. It's the purest form of that element, essentially. It's the very basic building blocks of whatever element we're talking about, all of which these are all made up of atoms. Technical troubles. There we go. So atoms are going to be composed of several different subatomic particles, and we're going to talk about the main subatomic particles. Again, with physics, we've discovered more and more of these subatomic particles, but the main ones you need to be concerned with are protons, neutrons, and electrons. So the dense little core of the atom is going to be called the nucleus, and it's made up of protons and neutrons. So protons are going to have a positive charge, while neutrons, as the name suggests, are going to be neutral. So they're going to have a neutral charge, no positive or negative. And then surrounding our nucleus, made up of protons and neutrons, are going to be these little tiny negatively charged particles called electrons. And these are going to move about that nucleus in fairly large space, and they're going to form what's called an electron cloud. It's going to basically be swirling around that nucleus. So even though their exact position really cannot be predicted or identified, specific groups of electrons are going to be more likely to move about within certain around certain regions of the nucleus. And these regions are going to be called electron shells. All right? So each electron shell is going to hold a very specific number of electrons, and it's not going to vary much. But if one shell is full, any additional electrons are going to move to other shells. So the first shell is going to hold 2 electrons, no more, and then the second shell of electrons is going to hold up to 8. And then our third shell can hold up to 18, and this can continue on depending on how large our element is and how many electrons it has. But those 3 shells are basically what we're going to need to worry about for the purposes of this class. So electron shells are going to be filled with electrons in a specific order, beginning with that first shell. So if an atom only has 2 electrons, those 2 electrons are going to reside in that first shell. However, if an atom has 3 electrons, there are going to be 2 electrons in that first shell and then 1 in that second shell. But that second shell can hold up to 8. So the number of electrons in an atom of an element is always going to be equal to the number of protons. All right, this is going to give it a net neutral charge overall. So that brings us then to atomic numbers and atomic mass. And this is just some vocabulary that you need to be aware of when we're talking about the different elements. So for starters, we have the atomic number, and this is just simply the number of protons in the nucleus of an atom. And so atoms of different elements are going to have different atomic numbers because they're going to have different number of protons. And this is essentially what's going to give each element its characteristics. The next term we need to be familiar with is mass number, and this is the number of protons and neutrons in an atom. So if we're looking at carbon, our atomic number is going to be 6. There are 6 protons in carbon, but the mass number is going to be 12. This is because we're considering both our protons and our neutrons. So 6 and 6 is going to be 12. For the atomic mass, we assume that the mass of these various subatomic particles is as follows. So neutrons are going to be about 1 Dalton. Protons are going to be pretty similar at about 1 Dalton. And then electrons are super duper tiny. They are 0.0005 Daltons. So they're very small and really don't contribute a whole lot to the overall atomic mass of an element. So as you can see here, our atomic mass for carbon is going to be 12.01. So just barely a little bit over 12, with the addition of these 0.008 and 0.007, brings us to about 12.01. And again, the electrons really aren't contributing a whole lot to the overall atomic mass of carbon. So the atomic mass, or the atomic weight, depending on what you want to call it, of an element is going to be the average mass of all of the naturally occurring isotopes. So these are atoms of an element. These isotopes are going to be atoms of an element that have different numbers of neutrons and are therefore going to have a slightly different mass number. So here with carbon, you can see we've got our 6 protons, but sometimes carbon can have 7 neutrons. Right? This doesn't impact the overall charge of our element of carbon because, again, neutrons are neutral, but it can alter slightly that atomic mass. And so because it is not terribly common to see a carbon with 6 protons and 7 neutrons, this is going to only cause that shift up a little bit for our atomic number. That's what's really going to contribute to our 12.01 for our atomic mass, because you do have to take into consideration the various isotopes for carbon. But again, like I said, 7 neutrons in a carbon atom is not terribly common, but it does happen. So it has to be factored into the overall atomic mass or the atomic weight. So here we look at how, again, like we mentioned with the electron shells, how we have the atomic structure, right? So hydrogen has 1 proton, no neutrons, and it's only going to have 1 electron in that first shell, right? This is going to help to balance out that charge, so hydrogen is going to be a net neutral charge, right? We then move on then to carbon, which again has our 6 electrons. We've got our 6 protons, 6 neutrons making up the nucleus, and then we have our first ring of our electron cloud, which again has those two electrons filling it, so it's a full first ring. And then our outer shell or outer ring is going to have 4. It's going to be, so 2 and 4 make 6. So this is going to have so carbon is not going to have a full second shell there. It's going to have only 4 out of the possible 8 in that second electron shell. This is one of the best reasons why carbon is so useful in the body, is because it is going to be very willing and able to bind with other, to form bonds with other elements, so that it can have that full 8 electrons in that outer shell, in that second shell. All right. And you can see here again with our, sodium here, we've got 11 protons, so we have 11 electrons, and then we have our 2 in the inner shell, 8 in our second shell, and then just 1 lonely electron in that third shell. So you kind of get the idea of how this organization of our electrons and those electron clouds works with regard to them swirling around that nucleus, essentially. So that then brings us then to ions, molecules, and compounds. And these are going to be, again, some just important terminology that we need to be aware of when we're talking about just general chemistry. So an ion is simply an atom that's going to have either a positive or a negative charge. And this is going to be caused by an unequal number of protons and electrons. So an atom that has lost or gained an electron, essentially. So ionization is going to be the process of either giving up or gaining that electron, which is going to cause that charge, essentially. And then an ion of an atom is going to be symbolized by its chemical symbol. So in the case of calcium, it's Ca. And then that's going to be then followed by either the number of positive or negative charges. So calcium an ion of calcium would be written at like this, Ca2+. So it has essentially lost or given up 2 electrons. This makes it positive because, remember, electrons are negative, so if you get rid of 2 electrons, you're making it less negative, so more positive. So a calcium ion is going to have a Ca2+. Is going to be how we would write that. All right, the next term we need to discuss is molecule. And this is just simply going to be 2 or more atoms that are sharing electrons, things like H2O. This is an oxygen with 2 hydrogens that are bound to it. And then a compound is going to be a substance that can be broken down into 2 or more different elements. So sodium chloride is a great example. If you add water to sodium chloride, it's going to dissociate or dissolve and dissociate into sodium ions and chloride ions that are all surrounded by H2O. In comparison to that molecule there, where this is going to take some sort of superhuman or great effort to cause these 2 atoms or these 3 atoms to shift or to dissociate from each other. All right, so that then brings us to chemical bonds, and these are really important because this is essentially what holds life together at its very base. So chemical bonds are very important. So these chemical bonds are going to occur when atoms are going to be held together by some kind of force of attraction. All right? And there's a couple of different kinds of attractions that we can talk about. So the number of electrons in the valence shell, that outer shell, or that second shell here, is going to determine the likelihood of an atom and how likely it is to form a chemical bond with another atom. Like we said, carbon is a fantastic example of this because it only has 4 electrons in its outer shell, so it's going to be looking to make bonds to have a full valence shell there, a full 8 in that electrons there, full 8 electrons in that outer shell, excuse me. So an atom with a valence shell that's going to be holding 8 electrons is chemically going to be very stable. So it's not going to be terribly willing to form bonds with any other atoms. These are going to be less common in the body because they're very stable. So biologically, they're not these. So biologically, these elements that have a full 8 electrons in their valence shell are not going to be terribly biologically important because they're not really going to be contributing a whole lot to the situation in terms of chemical bonds because they just don't want to get involved. They are happy doing their own thing. They have their electron shell is full and they just are minding their own business. So not great as far as forming chemical bonds, which are a really important source of energy. So under the right conditions then, 2 or more atoms can interact in several different ways that can produce a chemically stable arrangement of 8 valence electrons for each atom. And this is called the octet rule. So essentially it's just saying that in order to be stable, an element really likes to have 8 electrons in that outer shell. That just makes them happy, everything is stable and good. So different elements or atoms can interact in order to form that more stable arrangement and to meet that octet rule. So one atom is going to be more likely to interact with another atom if doing so is going to result in them both having those 8 valence electrons. All right. So we've already mentioned that ions are atoms that are is just an atom that is positively or negatively charged due to an unequal number of protons and electrons. So here you can see several of the really common ions that are found in the body. We've got hydrogen ions. This is a pretty common one. It usually has a +1 charge. Iron 2 and iron 3, just depending on what it's used for, is going to have a +3 or +2 charge. And then some of these anions or negatively charged ions are going to be things like fluoride, chloride, etc. And these have a negative charge. Those positively charged ions are called cations, while our negatively charged ions are called anions. Right? So because of this positive and negative charges that we're going to see with various ions, this is going to allow for something called an ionic bond. So like we mentioned, cations are going to be ions that are positively charged because they've lost one electron or an electron. Remember, so electrons are negative, so when you lose an electron, you're becoming less negative, which is going to be or more positive. Potato, potato, 6 of one, half dozen of another. More positive, less negative. And then anions, like we said, are ions that are negatively charged because they've gained an electron. So we bring in more negative charge, so they're going to have a more negative charge. These are anions. And then ionic bonds are going to be forces of attraction that are going to hold together ions of opposite charge. All right, so just like poles in magnets, negative and positive are going to attract. So any ionic compound that can break apart into its positive and negative ions in a solution, this is going to be called an electrolyte. So when you're drinking your Gatorade that has all those electrolytes in it, really the main electrolyte that's in Gatorade is sodium chloride. All right. So in this case, we've added some sort of solution. In the case of Gatorade, water, and it's broken that sodium chloride, that salt molecule. It's broken those ionic bonds, and you've got positively charged sodium ions, negatively charged chloride ions, just sort of floating around in there. All right. So as you can see, it's So that's our first type of bond, is our ionic bonds. All right. This is not a super strong bond. On the other hand, then we have our covalent bonds. All right. These are going to so our covalent bonds. This is going to be a bond that's formed by 2 or more atoms that are sharing electrons rather than gaining or losing them. like we would see in an ion, like in an ionic bond. All right, this is a much stronger bond. So when we share, everything is stronger. So covalent bonds, these are stronger than your ionic bonds. So atoms are going to form a covalently bonded molecule by sharing either 1, 2, or 3 pairs of valence electrons. All right. The larger the number of electron pairs that are being shared between those two atoms, the stronger that covalent bond is going to be. So something that is sharing 3 pairs, or has a triple bond, or is sharing 3 pairs of valence electrons, that's going to be a very strong bond. It's going to take a lot of energy to break those bonds. So things like 2 nitrogen atoms are going to be triple bonded, and they're going to be held together very tightly. In comparison to our hydrogen bond, which is just a single bond, this is not as strong of a bond. A double bond is going to be somewhere in the middle, obviously, like what you would see for O2, oxygen, which is what you breathe in, what you're breathing, or if you're like on one of those oxygen cannula things, this is what you're going to be breathing, is O2. So these bonds are formed because, like we said, everybody wants to have a full shell of electrons. In the case of hydrogen, there's not a whole lot that hydrogen's contributing, because each individual little hydrogen only has one little tiny ion all to itself, and so this H2, this single bond between 2 hydrogens, is going to allow for it to have that inner shell of 2 electrons to be complete. The same with oxygen. Everybody wants to have a full shell of electrons. So in this case, this double bond between oxygen here is allowing for a complete valence shell of electrons. So it's the full 8 there. So, okay, there we go. Come on. So there are a couple of different kinds of covalent bonds that can occur. So we have polar and non-polar covalent bonds. So in a non-polar covalent bond, there are going to be 2 atoms that are sharing electrons equally. So the one atom is not going to attract that shared electron more strongly than the other atom. Right? So everybody is sharing equally in the rotation, and they're sharing all equally in the electrons. Right? On the other hand, then we have a polar covalent bond. Right? This is when the sharing of electrons between 2 atoms is not even. Right? So one of the nucleus of one of those atoms is going to attract those shared electrons more strongly to the nucleus than the other. This is a great example of this is for water. This is a polar covalent bond here, right? So because the atom of oxygen is much bigger than the atoms of hydrogen, those electrons are going to be more drawn or more attracted to spend more time around oxygen. All right. So when a polar covalent bond forms, this is going to result in a molecular charge of a partial negative near the atom that's bigger, the atom that's more strongly attracting those electrons. So this atom is going to have greater electronegativity, and this is just simply the ability to attract electrons to itself more strongly. So oxygen is more electronegative than hydrogen. And because this polar covalent bond is made up of this very electronegative oxygen, these hydrogens are going to have a slightly positive or a partial positive charge around them, because again, those electrons aren't really spending as much time with the hydrogens as they are with the oxygens. So this is going to give the oxygen a partial negative charge, because more electrons, more negative more negative particles are going to be circling that oxygen, so it's going to be slightly more negative. All right, it's not going to have a full negative charge, but it's going to be a partial negative. All right, this is this little delta here. This is partial negative. All right, and like I said, those hydrogens are going to have partial positive. All right, partial positive charge. All right. The other type of bond that we can talk about then is hydrogen bonds, and this is going to result from attraction of oppositely charged parts of the molecule. So when we have our polar covalent bond, we again have these parts of our molecule that are going to have, or areas of our molecule that are going to have are going to be more positively charged or more negatively charged. And if we remember that opposites attract, the parts of this molecule, this this water molecule, around the oxygen is going to be slightly more negative, and around the hydrogen is going to be slightly more positive. So this slightly negative part of our water molecule is going to be attracted to the slightly positive hydrogen molecule, or is going to be more attracted to our slightly positive hydrogen ions, or hydrogen molecules. All right. So this is going to form something called a hydrogen bond. So these form when hydrogen atoms with a partial positive charge are going to be attracted to the partial negative charges in their neighboring electronegative atoms. All right. So like we said, the partial negative on our hydrogens is going to be attracted to our partial negative on our oxygens because opposites attract. So the result from this attraction of oppositely charged parts of the various of these different molecules is going to result more from this attraction of opposites rather than from either sharing of electrons, as you would see in a covalent bond, or from the loss or gain of an electron like you would see in an ionic bond. So these aren't terribly strong, but they're very important. This is what's going to give surface tension. This is what gives water its great surface tension. So that's a really important characteristic of water, especially. But yeah, and this hydrogen bonding is formed as a result of those polar covalent bonds. So hydrogen bonds between water molecules are going to give water something called cohesion, and this is just the tendency of like particles to stay together. And then hydrogen bonds are also going to create surface tension, which I mentioned before. So surface tension is just a measure of how difficult it is of the difficulty of stretching or breaking the surface of a liquid. So if you've ever seen in, like, I don't know, high school science class, where you take a penny and then you take a dropper and you slowly drop water on top of that penny, and it forms this kind of dome of water molecules, right? That's going to be because of the hydrogen bonds in that water causing or creating that surface tension. All right. If you add something like soap to it, or detergent, you're going to decrease that surface tension, and you're not going to get that nice dome or bubble of water. This surface tension is that difficulty of stretching or breaking the surface of that liquid. So now, we've talked about bonds. So chemical reactions is what we need to discuss next. And this is an important one also, because it's these chemical reactions that basically are going to fuel life, basically. So chemical reactions are going to occur when new bonds are formed or when old bonds are broken. All right. This is going to lead to either the production or the use of some sort of energy. So there are a couple of components that make up various chemical reactions. We have our reactant, which is what our starting substance is. So in this instance, we've got two H2s, two hydrogen ions, atoms, and then one molecule of O2. All right. So those are our reactants, our starting substances. And then our product from that chemical reaction is going to be the end substance, whatever you end up with. In this case, you end up with two molecules of H2O or water. So that's the product, is the ending substance. And then metabolism, we've kind of mentioned this in, I guess, chapter 1. This is just basically all of the various chemical reactions that are occurring in the body. So all of the breaking down and building up of all of these chemical reactions, these chemical bonds, are all going to contribute to the overall body's metabolism. So there are several different types or forms of energy with regards to this chemical reaction. So energy is simply, just plain and simple, it's the capacity to do work. So potential energy is just simply energy that's stored by matter due to its position. This is just energy that's being stored so that you can break chemical bonds later, and you're going to have that release of energy. All right. Kinetic energy is energy that's associated with matter that's in motion. It's moving, it's kinetic. And then chemical energy is a form of potential energy. This is going to be potential energy that is stored in a bond of a compound or a molecule. So we can break that bond and have a release of energy. So that brings us into the law of conservation of energy. And this states that energy can neither be created nor destroyed, but it can be converted from one form to another. All right. So the amount of energy that's out there in the world, in the universe, whatever, is going to be the same. It's just converted from one form to another. All right. Never going to be created or destroyed. All right. We're just converting it. All right. So that brings us then to energy transfer. All right. And there are a couple of things we need to consider here first. And so the first one is an exergonic reaction. All right. This is when a reaction is going to release more energy than it absorbs. All right. This is usually going to be a reaction that gives off heat. All right. And then we have an endergonic reaction, and this is going to be a reaction that absorbs more energy than it releases. These are usually going to feel cold. So the best example of an exergonic versus an endergonic reaction that I can think of, for an exergonic reaction, when you have those little hand heaters, that you use when it's cold. Not that it gets cold here, but you break the little packet and some sort of reaction occurs. An exergonic reaction is occurring that releases more energy than it's absorbing, and it gives off heat. All right, keeps your hands warm. All right. On the other side of that, on the flip side, we've got our endergonic reactions, which is going to be those crazy magical ice packs where, again, you break the contents of the bag and some sort of endergonic reaction occurs, and it's going to absorb more energy, so it's going to make that ice pack feel cold. So that is our endergonic versus exergonic reactions in everyday life, kind of. So with regards to these types of reactions or energy transfers, we have to talk about activation energy. All right, so this is the collision energy that's needed to break the chemical bonds of a reactant, of the reactants, and this is going to be the initial energy investment, if you will, that's needed to start a reaction. All right, so in order for this reaction to occur here, you can see this is the energy that's being used in our energy of reactants. Right, we're going to have an activation energy that's going to exceed the energy of that reaction. All right, so it's going to have to overcome the energy that's holding these things together. It's going to have to overcome it so that the energy of that product can be produced, so that we can break those bonds or cause whatever change or whatever reaction to occur. So this is our initial energy investment. This is like our our down payment for, we got to put in some energy so that we can have that reaction occur. All right. So in order to do this, we need something called a catalyst. All right. So in physiological conditions, with our body temperature the way it is and the concentration of these molecules that are just normally going to occur in our bodily fluids, this is going to be too low for most chemical reactions to just occur as quickly as we need them to in order to maintain life. So chemically speaking, we use something called a catalyst. All right. So a catalyst is going to be a chemical compound that's there to speed up that reaction by lowering the activation energy that's needed for that reaction to occur. All right. The catalyst does not in any way alter the difference in potential energy between our reactant and our product. Okay, so it's not changing the energy of the reactant or the energy of the product. It's simply reducing the activation energy that's needed for that reaction to occur. All right. Right. So it's just basically lowering the amount of energy that's needed to kickstart that reaction. All right. Okay. So now we need to talk about the various types of chemical reactions, because this is basically what keeps everything going in life. So we have several different kinds of chemical reactions to discuss. So first off, we have the synthesis reaction, and this is when two or more atoms, ions, or molecules, whatever you have, are going to combine to form a new, larger molecule. This is called anabolism, and it's typically going to be an endergonic reaction. Additionally, I should mention that the book has a really great sort of like visual depiction of the various types of reactions if you want to check that out. It's somewhere in chapter 2. I can't remember the exact figure number, but it's somewhere in chapter 2, which is available digitally, I should mention. Anyhow, so we then have our decomposition reaction, and this is going to be when something decomposes, it breaks down. So this is when this is going to be the splitting up of one large molecule into smaller atoms, ions, molecules, whatever. This is called catabolism. So remember, anabolism is adding together. We're synthesizing. We're having anabolism occur. We're synthesizing something new out of smaller parts. And then decomposition, it's breaking down, it's decomposing. That's catabolism. So anabolism is the adding together. Catabolism is the breaking down of things, or the splitting up, the decomposition. We then have an exchange reaction, and this is going to consist of both a synthesis and a decomposition. So basically, two components are going to break down and then rearrange and synthesize a new molecule. And then a reversible reaction is going to be where the product can be reverted to its original reactant, just depending on whether energy is added or taken away. All right, and then we have something called an oxidation reduction reaction, or a redox reaction, sometimes called. All right, so in the case of an oxidation reduction reaction, this is where these reactions are going to transfer electrons between atoms and molecules, and they're always going to occur in parallel. So when one substance is being oxidized, another is being reduced. So oxidation is just going to be the loss of electrons and the release of energy, and a reduction is going to be the gain of electrons and energy gain. All right, so these are always going to happen in tandem. They're happening together in parallel. All right, so that's why sometimes it's just shortened to redox, like reduction and oxidation, redox. So that brings us into our inorganic compounds and solutions. So inorganic compounds are typically going to lack carbon, and they're usually going to be a kind of more simpler molecule. So water is a fantastic example of an inorganic compound. This is going to be the most important and most abundant of the inorganic compounds in all living things that we know of today. So organic compounds are going to contain carbon and hydrogen, and usually you're going to have an oxygen sometimes, and these are always going to have covalent bonds. All right, these are going to be a huge deal in like biological chemistry or biochem, because this is basically what we're made of. Inorganic compounds are a little bit simpler. They lack that carbon, whereas organic compounds are always going to have a carbon, right? And then usually they'll have a hydrogen in there too. So, like we mentioned, water is the most important of the inorganic substances, right? So in a solution, a substance that's called a solvent is going to dissolve another substance that's called the solute. So if we're making salt water, we're making a solution of salt water. The substance called the solvent is being dissolved, so in that case it's the salt, like the table salt, and then the solute is the water that we add to dissolve that substance to make our salt solution, all right? So solutions that are going to be charged or that contain polar covalent bonds are going to be hydrophilic. They're water-loving. So hydro meaning water, philic meaning a lover of. So we have got philic and phobic. So if you have a phobia of spiders, you're afraid of them. So the hydrophobic would be water-fearing. And if, I can't think of any good philics, but hydrophilic is water-loving, right? So this solution so these solutions that are charged or contain those polar covalent bonds are hydrophilic, they're water-loving, and they're going to dissolve more easily in water, all right? Some, they're just going to mix nicely, all right? Molecules that contain mainly non-polar covalent bonds are going to be hydrophobic, all right? And they're going to be water-fearing, so they're not going to be very readily dissolved they're not going to be very water-soluble. This is like water, mixing water and oil. Oil is a hydrophobic thing. It's not going to want to mix and solubilize and dissolve in water. All right, so it's hydrophobic. All right, it's water-fearing. All right, so water is going to make a great solvent for lots and lots of different things. So the fact that the electronegativity that is found on the oxygen atom in water molecules, this is really great because it's going to attract things that are positively charged. So in this instance, we're talking about sodium chloride. So that electronegative oxygen atom in those water molecules is going to attract those positively charged sodium ions, and the electropositive hydrogen ions, those slightly positively charged hydrogen ions, are going to be attracted to those negatively charged chloride ions. All right. So soon that water molecule is going to surround and totally separate out our sodium chloride ions, our sodium ions and our chloride ions, and they're going to separate them from each other at the surface of the crystal, and they're going to break those ionic bonds that are responsible for holding the sodium chloride together. So basically it's dissolving, and when we're dissolving that salt crystal in water, it's breaking those ionic bonds, and it's essentially surrounding each individual sodium or chloride with little water molecules. So the water molecules that are surrounding the ions are also going to lessen the chances that sodium ion and chloride ion are going to come together to reform that ionic bond while that water is present. Right? So if you were to suddenly remove that water, though, our sodium chloride would not be buffered or surrounded essentially by our water molecules, and so they'd form back together. So if you've ever had a pot of water with salt in it, and then you accidentally just boil off all of the water somehow, you're going to be left with salt crystals in the bottom of that pan. This is because we've removed those that solvent, that water there, and these sodium and chloride ions are able to get back together to reform those ionic bonds and reform those crystals of sodium chloride of salt. So, water is also really important for some chemical reactions to occur. So water is a really great medium, like we've kind of already discussed. So there are two different types of reactions that are going to involve water. All right. So we've got our hydrolysis reaction, and this is where water is added to break a bond. So anytime you see the ending here, lyse means to cut or to cleave. So hydrolysis, this is going to be using water to cut or cleave or break some sort of bond. All right, so a hydrolysis reaction here is going to use water, where water is added to break a bond. All right, hydrolysis reactions are going to enable dietary nutrients to be absorbed into the body. So this is really going to be important for the breaking down of things, the breaking down of various molecules that can readily be absorbed into the body. On the other side, then, we have our dehydration synthesis reaction, and this is where we remove water to form a bond. All right, so that kind of makes sense when we break down what this is. Dehydration, you're dehydrating, you're removing that water, and then because of this removal of water, you have a synthesis reaction occurring. All right, so these reactions are going to occur during the synthesis of proteins and other big fat molecules that are going to be necessary in the body here. All right, so here we have our dehydration synthesis, where we have our molecules of glucose and fructose that are joined by our little molecule of water there. Right, we have our dehydration synthesis. I apologize, that was a mistake. We have our glucose molecule and our fructose molecule, all right, with our OH molecules on the end there. We have then a dehydration synthesis. We remove a molecule of water from these two molecules, and that causes a bond to form between the glucose and the fructose, producing something larger, which we know is sucrose. All right. On the opposite side of that, if we have a sucrose molecule, we can use hydrolysis, where you add water to this reaction. Right. So we're adding water, and it's going to break this bond here to produce our individual molecules of glucose and fructose. All right. So dehydration synthesis, we're removing water to form a bond. In our hydrolysis, we're adding water to break a bond. All right. So, water is super important on the earth, and because of its unique properties, this is what essentially allows life to occur on the planet. So one of the big things about water is its thermal properties, all right? So water is going to have a very high heat capacity. So this means that it can absorb or release a relatively large amount of heat with only a moderate change to its own temperature. This is going to be due mainly to the large number of hydrogen bonds that are found in water. So in order to heat a gallon of water, you're going to have to pump in a pretty significant amount of heat in order to change that temperature of that water, even just a little bit. You're going to have to pump it a lot to get it to boil, all right? So it has a high heat capacity, right? The other thermal property of water that's really important for life on Earth is going to be the high heat of vaporization. And this just means that it's going to require a lot of energy, a lot of heat to change water from a liquid into a gas, all right? So as water evaporates from the surface of the skin, like when you sweat, it's going to remove a large quantity of heat. So this is going to be a really important cooling mechanism for the body. It's going to kind of keep your temperature maintained at your comfortable, 97.6 or 98.7 degrees. It's this high heat of vaporization, all right? So both of those are going to be very important for sustaining life on Earth, and this is why water is so important in the world. All right, so water is also a really handy lubricant in the body. Water is going to play a major part of mucus and other lubricating fluids that are going to kind of keep everything moving smoothly in the body. And this lubrication is going to be needed to be found anywhere that there's going to be a lot of friction. So it's going to help to either reduce or eliminate the friction that is associated with anything that's occurring in the body. All right, next we have something called a mixture. So a mixture is simply a combination of elements or compounds that are going to be physically blended together but are not going to be chemically bound, all right? So three common liquid mixtures are going to be solutions, colloids, and suspensions, all right? So a solution is a substance, so in a solution, a substance called a solvent is going to dissolve another substance into a solute. So usually there's going to be more solvent than solute in a solution. So when we talked about making salt water, right? Our solution of salt water, right? Our solvent is the water that we're adding, and our solute is that salt, and there's usually going to be more water that you're adding than there would be salt, typically. This is not a hard and fast rule, but it's one of those things that's usually true. Next, we have a colloid. This is going to differ from a solution mainly based on mainly on the basis of size of its particles. So with the particles in a colloid, they're going to be large enough to scatter light. And then a suspension is going to be the suspended materials are going to be able to mix with liquid or air, are going to be able to mix with the liquid or the suspending medium, whatever it may be, for some time, but they're eventually going to settle out, all right? So suspensions, if you were to take like dirt and put it in a bottle of water and shake it up, you'd have muddy brown water for a little while. That would be a suspension. Those dirt molecules or dirt granules, whatever they are, would be suspended in our liquid. But if you were to give them enough time, it would all settle out and that dirt would settle to the bottom. That's a suspension. A colloid you can kind of think of like mayonnaise. It's going to be things are going to be dissolved, but they're not going to separate out eventually, and those particles are going to be large enough to scatter light. So you can't see through mayonnaise, essentially, is basically what it comes down to. So we then have to talk about some of the ways that we measure some of these things. All right, that brings us into percentage and molarity. All right, so percentage and molarity are just simply ways of describing the concentration of a molecule or the amount of that molecule that's dissolved in a solution. So a percent is going to give the relative mass of a solution that's found in a given volume of solution. So this is mass per volume. So for example, this is the number of grams of a substance per 100 mils of a solution. All right, that's how you calculate the percentage of a solution, right? And then another way that we can do this is with something called a mole, and a mole is the name for a number. Is the name for the number of atoms in an atomic weight of an element, or simply the number of molecules in a molecular weight of that type of molecule, and with the molecular weight being the sum of all of that, of all of the various atomic weights of the atoms that make up that molecule. So a 1 molar, or a 1 capital M, molar solution is going to equal 1 mole of solute per 1 liter. All right, so we calculate a mole of that based on, so a mole is we use the atomic weight of that element, or the atomic weight of that molecule, to calculate a mole, right? A molar solution, right? So if the atomic weight of an atom is 12, right? We'd have 1 mole would be 12 grams of solute per 1 liter, all right? All right. So just real quick, we're going to talk about acids, acid-base chemistry, and some salt chemistry, as well as pH. But I'm not gonna ask you about the pH for sure. We'll see about the acid-base stuff. So when molecules of inorganic acids, bases, or salts dissolve in water, they're going to undergo ionization or dissociation, and that is they're going to be separated into their individual little ions. So we talked about our sodium chloride, our potassium hydroxide, calcium or potassium chloride, whatever. This is an acid, a base, and a salt. All right, sodium chloride. Wait, no, potassium chloride. Excuse me. So, an acid. Acids are going to ionize into 1 or more hydrogen ions, right? So hydrogen chloride, we've got 1 or more hydrogen ions and 1 or more anions, those negatively charged anions, all right? So hydrogen chloride is an acid, all right? Don't get this on your skin. It's not good. It's really not good. So anyhow, we've got our hydrogen ion and our anion, our negatively charged ion, all right? This is an acid. This is what makes it an acid, right? A base is going to dissociate into 1 or more hydroxide ions, an OH, a negatively charged OH molecule, a hydroxide, and then 1 or more cations. These positively charged ions, and are going to be proton acceptors, all right? This is potassium hydroxide. This is a base. It's a very strong base. Don't get this one on your skin. It really does hurt. Personal experience. Don't do it. Bad lab safety. Anyhow, so this base, this is, once we just dissolve it into a liquid, it's going, like we said, we've got our hydroxide ion, our negatively charged hydroxide ion, and our positively charged cation, all right? And this is going to be something that's going to want to readily accept a proton, all right? And then last but not least, we have a salt, all right? And this is simply a compound that, a molecule that when, or I guess it is a compound that when dissolved in water is going to dissociate into cations and anions, all right? So we've got our cation, our negatively charged ion there. Excuse me, I had that backwards. Our cation, our negatively, oh my god, come on brain, I'm sorry. It's going to dissociate into its cations and anions, all right? Cations, all right, dissociates into its cations, positive potassium in this instance, and its anions, right, are negative chloride ion, all right? And neither of which is going to be a hydrogen or a hydroxide ion, all right? So it's just breaking down into its components. We're not ending up with any of this hydrogen nonsense, any of this hydroxide nonsense. It's just breaking down into its components, all right? So many of these salts are going to be present in the body and are therefore going to be formed when acids and base react with each other, all right? So that brings us then to pH. And I know there's a lot of like numbers and stuff happening on this slide, but don't get too freaked out about it. I'm not going to ask you too much about this for the exam because it's a lot. Anyhow, so pH. This is an important concept to understand, but you don't really need to know the math of it. pH is how we measure basically how acidic or how basic something is. Body fluids are mostly going to contain balanced quantities of acids and bases. This is important. You don't want to be a super acidic environment. You'd like eat yourself from the inside out. But biochemical reactions are going to be very sensitive to even these little small changes in the acidity or alkalinity or basicness of the pH of the body. So a solution's acidity or alkalinity, basicness, is based on a pH scale. And this is going to run from, it runs from 0 to 14. It also runs from this crazy thing right here. So a pH of 7, or 10 to the minus 7th, which is a lot of decimal points. Anyhow, you don't need to worry about that. A pH of 7 is going to be neutral, or equal numbers of hydrogen ions and hydroxide ions. All right, so neutral. This is things like milk. Any value that's below 7, all right, so anything from 1 to 6 is going to have a more acidic, is going to be a more acidic solution. It's going to have a greater number of hydrogen ions than it does hydroxide ions. And then alternatively, anything that's above 7 is going to be considered to be more alkaline or more basic. All right, so 8 to 14 is more basic. All right, so our potassium hydroxide, like I mentioned before, from up here, our potassium hydroxide, this is basic, right? This is going to have a pH of like 12 or 13. So this shit will burn a hole in your skin if you get it on you. So remember, practice proper lab safety. But anyhow, so this is basic, all right? Just because something is not acidic doesn't mean it can't really fuck your shit up. So important to keep that in mind. If something is acidic, it'll also really mess your shit up. Something that has a very high acidity, like hydrochloride, is also going to be very acidic. Also burn the crap out of you. So again, practice proper lab safety. But importantly, this neutral 7 range here is just going to be where we have an equal number of hydroxide and hydrogen ions. This is the happy zone where really not going to hurt you. If you pour milk on your skin, it's not going to bother it. If you pour hydrogen chloride or potassium hydroxide on your skin, you're going to be in trouble. So anyhow. So pH values. Here are this is kind of just an interesting little just an interesting little table looking at the different pH values for the various things, the various substances. So stomach juice is going to be between 1.2 and 3, a pH value of 1.2 and 3. So it's very acidic, all right? It's below 7. It's way below 7, right? This'll eat a hole in you. Except it's in your stomach, so it's contained and it's okay. Lemon juice is also going to be very acidic. Things like vinegar. Let's see. So vaginal fluid this is going to be about 3.5 to 4.5. And this variability is going to vary from person to person, but it's also going to vary. The acidity of this vaginal fluid is going to vary based on the menstrual cycle. Fun fact. So things like milk are going to be pretty close to neutral. It's going to be a 6.8. With distilled pure water, that's perfectly neutral. So blood is going to be just barely basic, just barely alkaline, not really too big difference there. And interestingly enough, semen is the fluid that's going to contain those little spermies from the gentleman. This is going to be a little bit basic too, all right? This is kind of this difference here in the various bodily fluids that can be mixed to reproduce, essentially. This difference here is going to be actually really important as far as like preventing like fertilization or fertilization basically, or it's going to help to keep those spermies out until the female's body is ready to release that egg and have that thing be fertilized. So this difference here is going to vary depending on when the female would be receptive to reproduction. Let's go then all the way down to lye. This is sodium hydroxide. This is hugely basic. This will burn the crap out of you if you don't dilute it enough. Like, it's very bad. So watch out for that. So last but not least, then we have buffer systems. All right, and these are really important. So buffer systems are used basically in just about everything you eat. So if you ever look at the one that I can think of off the top of my head is like, you know, that like Crystal Light or like that Country Time pink lemonade or whatever, those like drinks. They all have buffers in them, and this is going to help to maintain the pH. All right, so it makes it difficult for pH to change. All right, it takes a lot of effort in order to change the pH of that solution, essentially. So the pH values of different parts of the body are going to be maintained fairly constantly by a buffer system, and this is going to consist of a weak acid and a weak base. And the function of that buffer system is to convert strong acids or bases into weak acids or bases. All right, so it's just really going to help to kind of keep everything in the appropriate range. It just makes it so that you have to put in a lot of effort, a lot of very acidic stuff or a lot of very basic stuff to have any kind of change in your pH. Right? So one important buffer system in the body is something called the carbonic acid bicarb buffer system or bicarbonate buffer system. So bicarbonate ions is going to be written as HCO3 negative, and these are going to act as a weak base, while carbonic acid is going to act as a weak acid. I'm not going to ask you to know this crazy formula. Just know that the carbonic acid bicarb buffer system is important in the body. This is a lot. So anyhow, and that is all for part 1 of the chemistry lecture. There is a second part, so that'll be in a separate video though. So if you have any questions, comments, or concerns, please feel free to email me about anything, or we can talk about it in class. Just let me know. Also in this PowerPoint, I've included the cute little Wiley Plus interactive links. The little interactive links that I think are just really nice and helpful if you maybe don't understand something. So that is all I have for this particular lecture.